Hi everyone, today I'm going over topic 4.8, Introduction to Acid-Base Reactions. So acid-base chemistry as we know it today was independently developed by J.N. Bronsted and T.M. Lowry, who both proposed an idea of a proton donor and proton acceptor sort of model of acidity. And so there's a few definitions here. We have Bronsted, Lowry acids. These are proton, or H plus, like I was talking about in the last video, right? It's just a hydrogen that's lost its electron. Donors, as in they give an H plus. And then there are Bronsted, Lowry bases. These are proton acceptors. Again, H plus, not just a proton from any other molecule, but H plus specifically, acceptors. One important thing to note is that water can act as both a Bronsted acid and base, right? Because it's H2O, it can both give a proton, it can also receive a proton. It can give to make hydroxide, and it can receive to make hydronium, right? So you can have H2O, that can make OH minus by giving H plus, or H2O, it can make H3O plus by taking a proton. A few other important terms to define are conjugate acids, and this is the acid that is formed when a base takes a proton. And then similarly, the conjugate base is the base that forms after an acid has donated its protons, or its proton. Again, H plus. And so this right here is an example of a conjugate pair. We have our parent acid, HCl, our parent base, water, right? We said water can act as both an acid and a base. We have the conjugate acid, which is H3O plus. That's the acid that is formed after the reaction. And then this has gained a proton. This has lost a proton, so this is our conjugate base, right? Cl minus. One important thing to kind of look out for to help you figure out what's a conjugate acid and what is a conjugate base, especially if you're dealing with neutral at the start. If it is a positive charge, then that is your acid. If it has a negative charge, then that is your base, or your conjugate for each. So your conjugate acid base, assuming you're starting with a neutral parent acid and parent base, should be positive charge for an acid or negative charge for a base. That's just a helpful way of remembering it in case you can't figure out which one is which. If you start with neutral, in the end, right, your positive is going to be your acid, your negative is going to be your base. Now, an important concept for all of us to understand and remember is the idea of strong acids and strong bases. And so strong acids completely dissociate in water. Weak acids partially dissociate in water. And by that, I mean for a strong, once you put a strong acid in water, you get H plus whatever the conjugate base is, right, A minus, completely. With a weak acid, in water. After adding it to water, you'll get H+, you'll get A-, your conjugate acid, but you will also have some HA left over. Right, and so some of that original acid is still left over for a weak acid. For strong bases, they will dissociate to metal ions, or metal cations, and hydroxide anions completely. Similarly, weak bases only partially dissociate. And so if we look at our list of strong acids here on the left, you can see we have hydrochloric acid, HCl, hydrobromic acid, hydroiodic acid, HCl, HBr, and HI. We have chloric and perchloric acid, HCl3 and HCl4, nitric acid, and sulfuric acid. These will completely give up a proton. On the right are strong bases. We have two groups of those. We have the group 1A, metal hydroxides, lithium, sodium, potassium, rubidium, and cesium hydroxide. These completely dissociate to give M+ and OH-. And then we have our heavy group 2A metal hydroxides like calcium, strontium, and barium. These also completely dissociate. If it is any acid or base that is not on this list, it will not completely dissociate. And so you need to remember this list. Otherwise, you won't know if it's completely dissociating or not. Another helpful thing to keep in mind is that strong acids give weaker conjugate bases, and stronger bases give weaker conjugate acids. And in general, we always go from strong to weak. And so if, let's say in this reaction, I'll have strong acid plus strong base, and this goes to weak acid plus weak base, the reaction will always, or at least it'll prefer, to go to the right. Prefers to go to the weaker side. So I did mention in the last video as well that a reaction between an acid and a base is called a neutralization reaction, because you are neutralizing the acid and neutralizing the base to make water and salt. And so you can write these equations in a few ways. For example, if we take HCl, aqueous, plus NaOH, aqueous, that goes to H2O, liquid, plus NaCl, aqueous. Now in this case, for our terminology, this is our acid. It gives a proton. This is our base. It takes a proton. This is just water. And this is a salt. Right? When you neutralize an acid and a base, you make a salt. You can write this as a complete ionic equation. So we have H plus aqueous plus Cl minus aqueous plus Na plus OH minus will make H2O, right? We always keep liquids together, plus Na plus Cl minus. Again, we can cancel things out. Na and Cl both cancel out. And so our net ionic equation here is H plus OH minus makes water. And that's technically what the actual neutralization acid-base reaction is. We'll have a little bit of practice problems in class thinking about how we can use these principles, but for now, that's all. Thanks, guys.